Okay, welcome back. What I want to do is continue with the IEE Regulations, formulae part 3. Right, assignment B. Now just ignore the assignment B. It's only as, in this case, acting as a point of reference, okay? And I apologize. I've been an old man now, I don't have much teaching, so I will have to speak a little bit much slowly, okay? Right, not information given, right? Heater load equals 6 kilowatts. Type of device equals BS88 part 2 high rupture capacity fuse. Length of run equals 80 meters with 6 bends. ZD equals 0.4 ohms on TNS system. Calculate design current IB. Current demand equals power over voltage. Now, if you look back some of my videos before, you'll find that I've shown you how to do this before already, okay? But because this process appears again and again, it's always important to remember and apply that process. So you will need to write this out, make it your own. Get to know the formulation, okay? 6, where did the 6 come from? Times 1,000, why we use 6? What is that equal to? You'll find that that here is equal to this, okay? 6 kilowatts over 240 volts. Gives us 25 amps. Now, be sure you work this out for yourself, or you could simply say 6,000 over 240 will get you the same valuation. Okay. Since heater is instantaneous type, this will be the design current, IB equals 25 amps. Determine rating of device, IN, okay? And again, you're able to see what these are. Look back at the information in regards to part 1. Use table 8B. Now again, be aware here that table 8B may change, but what you're looking for is the rating values, okay, in regards to the design current. So this is just to allow for the factor if 8B is not your table, then you need to find the table for a design current of 25 amps. Okay, that is what I'm saying. Nearest fuse rating equal 25 amps. Check IN is greater than IB. Yes, values equal at 25 amps. Select phase conductor size. No correction factor to be applied. Okay. And again here using table 9D1 with installation method A enclosed. From table 9A, nearest larger size when IB equals 25 amps is equal to 4 millimeter cable. Okay. Now determine current carrying capacity, IZ equals 32 amps and volt drop equals 11 millivolt drops per amp per meter. Check IZ. Okay. Something else came across my mind then. It's greater than IN, and it is, yes. Now again, write these out for yourselves. Do not just try to read it from the screen. You guys I don't even understand how you guys learn these days without writing out anything. Oh, it's on my computer. Oh, but I can't take the computer in the classroom with me, can I? Oh yes, you blinking well can. What a shame. Oh goodness me. Write it out for yourself. Take it, use pen and the old-fashioned method, pen and paper. Okay. Voltage drop, permissible voltage equal 2.5% time. Now make sure that this is still the case, okay? Because there could have been any changes in that time, but I believe it still is 6 volts. Okay, obviously the actual voltage drop for cable times IB times length over 1000, and that is what you have here. Okay, equals 5 volts. So therefore, cable size satisfies voltage drop constraints. Okay. Maximum ZS can be obtained from table 41A. Again, confirm your tables, which will give a maximum 5 seconds disconnection time for the heater circuit and satisfy protection against indirect contact requirements. Okay, now again, from table 41A, confirm the correct tables you're using. Determine these values, and if there's any changes in those names given. Okay. Determine size of CPC and check thermal constraints. In order that the actual ZS value can be determined, an estimate of the CPC size has to be made and its resistance value applied in the formula. Okay, ZD 0.4 ohms given to find R1 plus R2 from table 8D. When the phase conductor is 4 mm, try a CPC size of 2.5 mm. And you would probably find that 2.5 mm will actually be sufficient. Okay. Actual ZS equals ZD. This you can do for yourself. Actual ZS equals ZD plus R1 plus R2 equals 0.4 plus 0.324 ohms equals 0.724 ohms. Okay. So let me just make sure I bring this into square into online. Okay. The actual value of ZS is less than the maximum value, and this circuit would comply with the shock protection constraint. To ensure the most economical installation, further calculations could lead to a smaller CSA of CPC than 2.5. Sorry, but I would recommend sticking with the 2.5. It allows for any future development should the system change for whatever reason. Okay. So they're saying here that 331.5 amp would flow should a fault occur. Would the earth conductor handle that? Disconnection time obtained from figure 9 appendix 8 4BS 88 part 2 field. Now be aware of any changes within these parameters. Okay. 31.5 amps is 0.02 seconds. A check now to ensure that the cable is protected formally using the equation in regulation 543-2 with the value of K equals 143 obtained from table 54B. Now again, confirm your tables are functional in regards to finding K. And cross-sectional area equals S equals I squared times T over K. Yes, okay. Make sure you write these out and you can familiarize yourself with them fully. The nearest conductor size for a previously insulated cable is 1 mm square from table 8D. Okay, phase conductor, etc., 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 etc. That's for you to read out for yourselves. Then actual ZS equals ZD plus R1 plus R2. Now again, write out the formula. Make sure you're putting in the information that you have. And again, use your on-site guide to provide you with additional information as to how the process is carried out as well. Okay. And so I'm just looking for something here that I'm looking for. Just bear with me for a second. I don't see it here. Just trying to see why. Okay. Clear the background. Now look at how they've got this figure here. Okay. Because that is very interesting. And see what they're saying here. Now when you do this, does it come up to this? That's what I would like you to determine for yourself. Make sure you are equated with it. Using the adjusted value of ZS, value of IF and S can be calculated. Okay. If IF equals to voltage over ZS, etc., and it's 2035 amps. Do the calculation for yourselves. Okay, it's important. And here we're looking at time t constant. So time t, it's okay, it just came out of my, not as a constant. Figure 9 equals 0.07 seconds, sorry. Bring that into play. That's what you have here. Make sure again that you know how to get to this equation here, to this figure here. Okay. Because what I'm finding here is that let me just try something a second. 1 second. Let me see if this comes out the way I think it should come out. Okay. Now bear with me. 2, 3, 5. One second, bear with me for a second. I'm just trying something here for myself to see. Okay. That's interesting. Now you see, that's why I said to you to do this yourselves, so you can be sure you arrive at the correct solution. Okay. Now okay. Oh, that's interesting. Could be me, but look, be aware that there may be errors in this. Okay. Be aware that there may be errors in these calculations here. I'm not quite happy with this process at the moment, so well, I'm going to leave it for you to look for it yourself and see what you think needs to be done. Now again, use your on-site guide. Make sure you follow that process, okay? Okay. No, still not happy with that outcome. So make sure that your process for this calculation here is worked out correctly. Of course, this 62.2 I am questioning but it's possible that I'm doing it the wrong process. Okay. Because it's clearly states saying that you will need to multiply 235 squared, not squared, yeah, 235 squared, not square rooted at this point in time, times 0.07 over 143. Then you find the square root of the total. I'm having a little calculus problem here with this. I'm not happy with that outcome, but maybe it's me doing it wrong. Maybe I'm missing something. Now this is just some additional work here for you. Okay, and just additional work for you to do for yourselves. Okay, and here we have a summary of answers. Okay, and that's where I'm going to stop for now. Okay, so thank you for your time. I hope you've enjoyed this. Now make sure you write the information out and you do the calculations. The process must be understood, okay, at all times. Okay, I'm stopping there now. Okay, and we'll continue next time on. Thank you. Bye bye for now. Have a good day. Bye bye.